Yeah, I wanted to talk to you today about one application of the field of scattering amplitudes, which is sort of the one that motivated Zvi and David and me to get interested in this subject quite a while ago. And that is their application to the study of physics at the energy frontier, where the highest energy collisions made by man are taking place. And those are generally these days at hadron colliders. And the principal hadron collider right now is the Large Hadron Collider, which collides protons together. And it's exploring this energy frontier. And in order to make the best use of this collider, a lot of theory is needed, basically to understand what the standard model, which was mentioned by Lorenzo, predicts in order to try to uncover new physics that goes beyond the standard model. So I want to tell you some of that story today. So here's a picture of the ring, or where the ring is, that represents the Large Hadron Collider. It's 27 kilometers in circumference. It inhabits 2 countries. That yellow jagged line there is the border between France and Switzerland. And France is on the left, roughly. And Geneva, and the Geneva airport you can see on the right. And the protons circulate around this ring after building up their energy in smaller rings that you can also see there. And there are a number of collision points where they undergo very violent collisions. And you can see at least 4 detectors listed there. And the ones that are more interesting for my talk are Atlas and CMS. And they are really exploring the highest energy collisions that you can make in a controlled situation in the laboratory. And this machine represents an increase in capacity over previous machines in 2 ways. One is in the energy. Its center of mass energy is 13 going on 14 in a few years, tera electron volts. For comparison, the mass of the proton is about 1 giga electron volt, or GeV. And so the rest energy in this collision is about 14,000 proton masses. And so you can make a lot of particles in such collisions, and you might be able to make very heavy new particles. Another way in which this is an advance over the Tevatron, which was a machine at Fermilab in Illinois, is in the collision rate, or the luminosity. This machine produces 100 times as many collisions per second as the Tevatron is capable of doing. And so those 2 things give it a new window that lets us explore physics at the shortest distance scales. And it's been operating since 2010, or about a decade. And in the past 8 years or so, it's been working very well. It's exceeded the design performance in terms of the number of collisions per second. And what you see here is something called the integrated luminosity, but that's directly proportional to the number of proton collisions that it's accumulated and been able to study. And the more collisions you have, the better your data, the better your statistics, the more precisely you can measure things, the more you can look for the unknown. As you can see in the early years, it took a little while to get up to this high collision rate. But in the last 2 years, 2017 and 2018, it was producing a lot of data. The unit used here by particle physicists is called inverse femtobarns. It's a pretty funny unit, but the way to remember is that if you have 60 inverse femtobarns, you can see one event. It's at a cross-section is a probability for a collision taking place, and it has units of area. And a barn is only 10 to the minus 24 square centimeters, so that's pretty small. But a femtobarn is 10 to the minus 15 of that. So we're talking about 10 to the minus 40 times the size. That's the kind of probabilities for things happening that we can look at with this machine. So Lorenzo mentioned the standard model, and that's our basic framework for understanding everything that happens at the Large Hadron Collider, and in most of the particle physics. And what the standard model does, in very brief, is it puts all of the elementary forces that we know about, except for gravity, into the same basic framework.
And the particles of the Standard Model, excluding the Higgs boson, can be laid out in a kind of pattern like this, where these guys here are the particles of matter. The up and down quarks live inside the proton. The electron, you know, from its role of carrying electrical currents and so on. And then there are heavier cousins of the same particles that have very similar properties except for their masses, which usually cause them to decay very quickly. So these are in the province of accelerators. We only really see them there pretty much. Then there are the force carriers, and that includes the photon for electromagnetism and the weak bosons, which are W's and Z's for the weak force. And then the gluon. The gluon is the carrier of the strong force. The guys up here, the up and down quark and their cousins, the heavier quarks, they all feel the strong force. And that strong force binds them in ordinary matter into nucleons, into protons and neutrons, and also a little bit heavier particles or other particles called mesons that decay. And we have a basic picture for all of these forces in which we describe them using Feynman diagrams, which we'll come back to later, but their essence can be described by a single Feynman diagram, which describes which particles they talk to. For example, electromagnetism talks to electrons, not surprisingly. So there's a vertex in a Feynman diagram that describes this coupling. But it also talks to quarks because quarks, like electrons, are electrically charged. The weak bosons talk to many different particles, in fact, basically to all of the matter particles, and they cause things like radioactive decay. So a decay of a proton to a neutron plus a positron and a neutrino could be described in this way, moving upward in time. And then the strong force describes the interaction between quarks in QCD. And because the strong force is strong, it's the main player in LHC collisions. We often are interested in looking at things that are related to the weak force, but the strong force produces huge backgrounds that we need to understand very well. And as was mentioned by Lorenzo, the crowning achievement of the Large Hadron Collider to date has been to discover the last missing particle of the Standard Model, the Higgs boson, which was proposed in 1964, and it took almost 50 years to discover it. The discovery was announced in 2012. Here is some of the evidence that led to the discovery. What is shown here is plots from the two detectors participating in the discovery, ATLAS and CMS, and it shows the invariant mass of two photons. So you detect two photons coming out of the collision, and you add up their energy and momentum, which relativistically are a 4-vector, and you can combine them and construct an invariant called the gamma-gamma invariant mass. And if it's a Higgs boson, it should peak at a particular place, and you can see that it does. It peaks at about 125 GeV, or 150 times the mass of the proton, roughly. And so that is evidence of this new particle. You'll notice that it's not background free. There are a lot of particles, a lot of photon pairs that have nothing to do with the Higgs boson. But and they're produced by what we call sort of QCD processes, quark-anti-quark annihilation. Anyway, they produce a smooth falling background, and you can identify this bump on top of the background. That is actually one of the cleanest ways to see the Higgs boson. There is one other clean way, but the Higgs has been seen in many other ways, many of which are much dirtier or harder to extract. So this is one of the cleanest signals for the Higgs. Now, as I mentioned, the Higgs was predicted in 1964, and two of the theorists were around to celebrate, Francois Englert and Peter Higgs, and they received the Nobel Prize soon after this discovery, which the experimentalists were glad to provide them with. So that completes all the particles of the Standard Model. But we know the standard model isn't the final answer. There are a lot of questions that it doesn't answer properly. And one of the questions it doesn't answer, it doesn't have a candidate for dark matter. We don't know for sure that dark matter is an elementary particle. It might be something much more complicated. It might be made out of elementary particles in some other sector, or it might be a single kind of elementary particle. But if there is an elementary particle, and if it has something to do with the weak scale, the scale at which the W's and Z's get their mass, the LHC might be able to produce it, or produce some other particles that decay to it. This is some evidence for dark matter in the galactic rotation curves. As you move out and you calculate the forces from the visible matter here, you expect the velocities of galaxies to be on this curve, but instead they're much higher. And there's pretty compelling evidence for dark matter, not only in the halos of galaxies, but also between clusters of galaxies. This is a collision between two clusters called the bullet cluster, which shows that the collision has moved the ordinary matter in red and separated it from the location of the dark matter as inferred by gravitational lensing. So there's pretty compelling evidence that dark matter is out there, and it would be great if we could produce it in the laboratory. So the LHC has been searching for dark matter. Now, it's also been searching more generally in the context of physics beyond the standard model. There's a theoretical problem with the standard model, which is called the hierarchy problem. In the standard model, the electroweak scale, the masses of the W's and Z's look very fine-tuned if you could imagine going to energies much above them, to thousands of TeV. And in other words, if you try to calculate and you put a high energy cutoff of 1,000 TeV, typically the Higgs potential that you get causes the Higgs and W masses all to rise up near the cutoff. And so it's a puzzle, and many theories have been developed to try to solve this puzzle, and they all have to, essentially, almost all, have a host of new massive particles with masses that are within reach of the LHC. So that was one of the compelling arguments, besides the Higgs boson, to build such a collider. Now, you can suppose this red particle is a new particle, and suppose you could produce it singly. This is actually difficult because then these effects typically disrupt precise measurements in an electroweak sector. And so it's much more likely that these new particles should be pair-produced. Then their precision electroweak effects are much smaller. And so such theories often have a discrete symmetry that tells you you can't make the new particles one at a time, you have to make them two at a time. In that case, if there is such a symmetry, then the lightest particle that it carries a non-trivial odd quantum number under that symmetry becomes stable and could be a dark matter candidate. So there are a lot of theories out there that contain within them dark matter candidates. One of the types of theories is called supersymmetry, but there are other flavors of new physics at the LHC that could be seen at the LHC. And if you want your theory to make a big dent at the LHC, you usually have some colored particles around. Also, the colored particles help in the hierarchy problem. They could cancel the effects of the top quark, which is also colored. And that is, has the strong force. And these colored particles, because they carry the strong force, they will have larger cross-sections, and they might decay to dark matter, but they would have to also decay to standard model particles like quarks and gluons, and in general, different models can produce sort of all the particles of the standard model, plus potentially dark matter. More generally, you never see the new physics particles directly. They're either very stable or very unstable, and so you typically just see their decay products. And so then you need to distinguish their decay products from this production in the Standard Model. Now, one example that has been studied and searched for a lot at the Large Hadron Collider is a theory called supersymmetry. In this theory, there's a symmetry between matter, made out of fermions, and forces, which are carried by vector bosons. So it relates spin 1 to spin 1/2, and also to spin 0. So every integer spin particle, or boson, has a spin 1/2 partner. And so there have been many searches for the particles of supersymmetry at the Large Hadron Collider, and indeed at many other machines. But these searches are not free of backgrounds. There are always Standard Model cross-sections that look very much like the new physics cross-sections. One example, this is sort of a classic signature of dark matter within supersymmetry. You can have two protons come in, and because these particles, gluinos, they are the partners of the gluons, and they have a very big color charge, so if they're light enough, they will be produced very copiously. There will be lots of gluinos. But the gluinos will decay. They actually have to get rid of their color charge, because the lightest supersymmetric particle, which would be a WIMP or an LSB, it has no color, it only has weak interactions. So the gluinos have to get rid of their color, and they can do it by radiating two quark jets. And so you get what's called a SUSY cascade, and you get two quark jets. But then you also get these very light particles, these lighter particles, lighter supersymmetric particles, but they escape the detector, so you don't see them directly. Instead, if you look at the detector from the point of view of the beam going into the screen, you see four jets come out, and they're imbalanced. So the momentum was conserved, but some of it was carried off by invisible particles. So this is called, for some reason, missing transverse energy, or MET, plus four jets. So that's a very canonical, very standard way to search for supersymmetry at the LHC. And it would be great if that was the only thing that could produce such an event, but it's not. Quite often, you make a Z boson at the LHC. We'll see in a second, there are huge cross-sections for Z bosons. And it's not that costly to make them in association with quarks or gluons, which will turn into jets. So here's an example where a quark and an antiquark annihilate. There are a bunch of Feynman diagrams inside this blob, and you produce a Z boson along with these four hadronic jets. And then 20% of the time, the Z boson can decay to neutrinos. And when it does this, the neutrinos escape the detector, and it disappears, and it looks just like a pair of LSPs. So this is what we call an irreducible background. There's no way for the experimentalist to tell the difference except by understanding this precisely. There are many other backgrounds that are similar but reducible. In other words, if you make a mistake, it looks like MET plus four jets. So this precision theory and calculating to higher orders in the strong coupling constant can help with this. And so this is just an example of how sophisticated these supersymmetry searches are. What this shows is dozens of different searches, in this case with the number of jets along with the missing energy being 4. And they've also have similar plots, which I won't bore you with, for 1, 2, 3, 5, and 6 jets going along with the MET. And so every point here is where they have measured a rate, and they have compared it to their estimate of the background. In green is the reducible backgrounds in red, and then there's this irreducible background from Z to neutrinos, which is actually the biggest because this is on a logarithmic plot. So all these measurements, they agree with the background predictions, and they involve some theory and also some experimental techniques to determine them. But what you can see is that the number of observed is equal to the number of predicted. everywhere they look. And there are hundreds of different sort of sub-measurements in here. So there are no excesses, otherwise you would have heard about it by now. And so instead of saying we've discovered supersymmetry, they set lower limits on the masses of the gluinos and other superparticles. So as an example, from the same paper, and CMS was able to make some exclusion plots that look like this. So they depend on both the mass of the lightest of the WIMP of the LSP and on the mass of the gluino. For example, if the mass of the LSP is very light, they exclude gluinos up to almost 2,000 GeV or 2 TeV. That's pretty incredible from a machine that's operating at 8 to 13 TeV, because they're using up an awful lot of the proton's energy to make these particles, except they weren't actually making any in here. And there are various decays, so you can look at the vanilla jets that come from QQ bar. You can also ask if the jets have B particles in them, and then you can get slightly better reach, especially when the LSP is heavier. So that's just one example, and combining these and many other searches, there are a huge number of different searches that have been carried out. You can't even read this to know which one, but on the bottom here's the mass scale, and the mass scale corresponds to different kinds of particles. The gluino reach is typically the heaviest, but some of the other supersymmetric particles can be bounded for a while, out to hundreds of GeV. So supersymmetry isn't there, but it could still be there at slightly heavier masses. And the LHC is poised to collect much more data over the next couple of decades. So you should still watch this space. But at the same time, since there is no convincing evidence for supersymmetry or any other direct production of new particles, the other way to look for new physics is looking sort of closer to the standard model, looking for making measurements and looking for deviations in rates. And this can be the old particles of the standard model, or they can also involve the brand new Higgs boson. Studying its properties is going to be a big task of the LHC in the coming years. These measurements are actually a lot trickier than searches. You have to calibrate everything properly, and they take a while to perform. Also, they place more demands often on the theory to go to higher orders. So I want to show you some of the standard model measurements that have already been made by the Collider collaborations. Just happened to choose Atlas. CMS has very similar ones. And what you can see is that there's a huge range of cross-sections. Up here is the total cross-section for PP, and it's about 12 or 13 orders of magnitude higher than some of these extremely rare processes. So there's an incredible collision rate, and you have to actually dig out from under it to find all of these much rarer processes. But they include things like W's and Z's. Those are very large cross-sections. In fact, they've measured we were talking about Z production in association with 4 jets. That's this process here. It's been measured, and the blue is the uncertainties in 2015 on that rate, and they even measure down to 7 jets. And then the gray bands are the theory predictions. And usually theory is ahead of experiment, in that the theory bands are a little bit more narrow or more precise, but experiment is improving and theory needs to improve too. Over here is Higgs production. The Higgs has been seen, and this is its total cross-section, but that gamma-gamma rate I showed you, that's only part in 10 to the 3, 2 parts in 10 to the 3 of the Higgs production. And so if you include this probability of going to gamma-gamma, it's actually much, much lower. There are other processes involving the heaviest quark. That's another place where new physics could be found. The top quark. They make millions of top quarks now at the LHC, so they can measure the total production rate rather precisely. And then there are ones that involve multiple electroweak bosons. At the time of 2015, mostly there were two-body final states in a double electroweak, like two Z's, or W and Z, or Z and photon. And there wasn't so much with larger numbers. But now the most recent measurements are really from 2019, and they include, well, they didn't bother showing all the Z plus jets anymore, but they are now measuring things with three electroweak vector bosons that have very tiny cross sections, especially when you take into account the decays of the W's and Z's to things that you can see well. And more things have been measured from the Higgs. Another way of producing the Higgs has been measured here. So now I want to turn a little bit from the experiment to the theory. And I want to talk about the framework we have for making all of those theory predictions. So at the core, the basic reason we can make such predictions at all is something called asymptotic freedom. When we study quantum field theories at different distance scales, we find that the coupling strengths depend logarithmically on the distance. In QED, if you are at distances much shorter than the Compton wavelength of the electron, you make electron pairs in the vacuum, and they polarize the vacuum and change the value of the QED coupling, which is called alpha, or 1 over 137, so that it runs with energy. The same thing happens in QCD, the theory of the strong interactions. The gluon self interactions depend on a parameter called the strong coupling, alpha S. But they run in the opposite direction. There is a diagram, the gluon polarization of the vacuum, because the gluons carry charge themselves and have spin 1, it turns out that it has the opposite sign from the polarization effect of the quarks, which is the same as in QCD. And because of this opposite sign, the running is such that when you go to shorter distances, this coupling becomes smaller. When you have a small coupling, you can use perturbation theory. You can use things like Feynman diagrams. And so then the theory becomes calculable. At very small momenta or long distances, then the theory becomes extremely strong, and you can't calculate it very well except using techniques like lattice gauge theory. And in this regime, the quarks are bound into the proton. Over here, at very short distances, they don't see the size of the hadrons. Instead, they are almost free, and that's why we call it asymptotic freedom. This running is logarithmic, so it becomes very slow out here. So although it's running, this constant is roughly 1/10 at scales that the LHC is operating at. So once again, at long distances, things are confining. At short distances, they're calculable. At long distances, we have the proton itself coming into the collision. Also, when the collision we can describe in terms of quarks and gluons, but as they emerge from the collision, they do so in jets or sprays of hadrons. At the end of the day, these quarks and gluons confine and turn into hadrons. We can't really predict this precisely, this confinement. We can just model it a bit. And this is the part that we can do more precisely. So to show this picture again a different way, there is a way to factorize or separate the problem into different pieces. And this is called QCD factorization, and it's strongly related to the parton model, which describes the structure of the proton in a particular way, that it's like a flashlight containing a beam of quarks and gluons. And whenever you have a suitable proton collision, you sort of sample one parton at a time, and you need to know a probability of finding these quarks inside the proton. But given a knowledge of that structure, then you can multiply those probabilities by another probability, which we call the short distance cross-section, to produce something and there are certain restrictions on it. It should be something called infrared safe. But for example, the prediction of a z, which you would see by its decay to e plus e minus, can be done in this way. So you have to take certain functions called parton distribution functions from experiments, and they're known to a few percent now through a lot of hard work. And then the theorist's job is to calculate this probability here, which is a sort of imaginary scattering process that takes place in the femto universe because it's at distances that are shorter than a femtometer, or 10 to the minus 15 meters. Actually, there's some arbitrariness where you draw this box, and that's called the factorization scale. So you might play with that a little bit to see how accurate your predictions are. And this box, this probability in here, we call it the short distance cross-section, and put a little hat on it. And we know pretty much all the standard model parameters that go into it. Alpha S isn't known perfectly, so it depends a little on alpha S. But it also depends on some artificial scales. This factorization scale is not a real scale. And there's also a renormalization scale. And so you can vary those a little bit to estimate the uncertainties in your calculation. Let me just, and the general thing you do is you expand the short distance cross-section in terms of powers of this relatively small coupling, alpha S, and it depends on what scale you evaluate it at. Depending on the process, you might have different powers of alpha S at leading order. I'm going to show you an example of Higgs production where this is 2, and then there are extra terms that come when you work harder and go to higher orders in alpha S. And as a result of combining these terms, you get more accurate predictions. So you might think that leading order would work okay if alpha S is a tenth, but actually these terms are very large, and you get very poor convergence until you go to higher orders. And depending on the process, you have to go to higher and higher orders. This is essentially the worst case process, the production of the Higgs boson through gluon fusion, which we'll come back to at the end. But it depends on the LHC energy, so the later runs of the LHC have been at higher energy and have higher cross-sections. But this is the leading order prediction, and this is the state of the art, next to leading order. And you can see that the leading order uncertainty estimate is not good at all. The actual answer is up here, nowhere near here. So you really need to go to at least NLO before you have any idea what the cross-section is. And at this point, you're still 20% uncertain for this. In some cases, maybe it's better than that. So anyway, the further you can go, the better prediction you can get. And all these cross-sections for the Higgs fold into our understanding of the Higgs properties and how it couples to all the other particles of the standard model. So to do that with precision, we really need to have these very precise predictions. So now under the hood, to produce these short distance cross-sections, I guess I should have put a hat here, sigma hat, they are a function of something we just generically call the S matrix. And it's not the supersymmetric S matrix. In the real world, it seems to be just the ordinary S matrix. But anyway, the answer is a function of S matrix elements. So we need to have tools to compute all these S matrix elements. And the first thing we need to do is compute the lowest order matrix elements. And those are what we call trees, because we can write down Feynman diagrams for them, and they have no closed loops. Here's a very simple tree which is for producing the Z boson in quark-antiquark annihilation, and then its decay to electron pairs. Now, there are also multi-jet production through gluons that require much more complicated trees with many more Feynman diagrams, but they're still relatively simple, and as you can see here, you can use textbook methods to study tree diagrams. But we want to go further. Trees only will give us the leading order cross-sections, and those are really bad in terms of precision. So we need to go to next to leading order. And in order to do that, one of the ingredients we need are loop amplitudes. So here's an example of a loop amplitude, one loop, and this one is one of the ones that contributes to that background process I showed before, z plus 4 jets. So this is where the fun starts, because using textbook techniques for loop diagrams like this is really too slow, even when you program it with computers. You need to reorganize things to try to make things much faster and more stable. So this is not the only thing you need for NLO. You also need to have tree diagrams with one more parton. So here is a loop diagram for this very simple process of Z production. But at the same order in alpha S, you need to square processes with extra gluons or quarks in them. However, these were the bottleneck for a long time, and we had to produce these in the early days in an artisanal way, one at a time. But now, through the work of many people, we know how to mass produce these loop amplitudes. Here's an indication of the challenge. If you want to produce, for example, a weak boson and n gluons, here are all the Feynman diagrams. And by the time you get to one loop and 3 gluons, you can't even resolve them on this plot. We were able to push these methods with V and David and our collaborators as far as producing a W, this blue item, blue line, and 5 more jets. And the Feynman diagrams required for that were about 250,000, but we didn't use Feynman diagrams. We used another method, which I'll outline to you now. We actually went back to the 1960s. In the 1960s, QCD was not yet understood. There were many strongly interacting particles. People didn't know whether field theory would even work for this kind of problem. And so they were using more general properties. There was a bootstrap program based on the analytic properties, or what we now call on-shell information, because the only particles you put in are those that are external on their mass shell. And there was a lot of developments in there which they weren't able to make enough assumptions, and so they couldn't go all the way, but they had a lot of the right ideas. And one is that the basic properties of the S matrix are controlled by its singularities, just like singularities of functions in a complex plane. And the two kinds of singularities that you're used to in the complex plane are poles and branch cuts. The poles, in terms of the S matrix, correspond to regions where you can separate a scattering process into two processes that are almost disconnected. They're only connected by one light state propagating in between the two scatterings. And then there are branch cuts. Branch cuts arise when you have pairs of intermediate states, or maybe 3 or 4 intermediate states. In that case, when you move the scattering momentum from below threshold to above threshold, you get a discontinuity. It's a generalization of the optical theorem. Now, in fact, this analyticity fell out of favor in the 1970s once a Lagrangian for QCD became available, and people switched to Feynman rules. But eventually, to do more and more complicated processes, the Feynman rules became extremely tedious and cumbersome and not fast enough. And so we worked to resurrect some of the early ideas of analyticity and unitarity in order to compute these amplitudes in perturbative QCD for use at the LHC. Now, we had more information than they had in these days. We had underlying information about perturbation theory that could assist the analyticity. So one other sort of key philosophical point is that when you have a small number of Feynman diagrams, it's like having a small number of grains of sand in your hand. Each one does something kind of important, and it's useful to think about them one by one. But when you go to hundreds of thousands or millions of Feynman diagrams, they don't really mean much by themselves. It's more acting like a fluid, like if you were to pour the sand out of your hand. And so not thinking about it in terms of individual diagrams, but thinking of just how these blobs which represent the sum of all the diagrams, move around, is a more practical way to think about things. There's also some miraculous zeros that happen in QCD at tree level, which we can exploit when we go to higher loops. For example, if we assign helicities to the gluons, it's been known since the 80s that if all the gluons have the same helicity, or just one of them has the opposite helicity, then you get exactly zero. And if exactly two of them have the opposite helicity, you get a very short formula in terms of some variables I won't bother defining, but there's an extremely short one-term formula that captures all of these very large number of Feynman diagrams. So when we use analyticity, we can recycle these simple formulas at tree level into simple formulas or fast evaluations at the loop level. So here's just a sketch or a little movie about how it happens. We want to take a scattering amplitude like this, and we want to do an analytic continuation of some type. That is, we want to change the kinematics smoothly and find simpler regions. So we move around in the kinematics, and then we discover some region where the amplitude falls apart into simpler ones. And maybe we already know what these are, and then we know the residues at this pole. And we can go find the residues at other poles by moving around in different ways. And when you carry out that picture, you get something called the BCFW recursion relations, which Lorenzo mentioned before. I didn't bother writing them down, but they basically write a complicated amplitude as a sum over products of simpler amplitudes. And they're recursive, so you can go from smaller numbers of particles to larger numbers. And it's all very straightforward. You can implement it very fast on it numerically too if you want. So these are examples of trees being recycled into more complicated trees. In fact, you can go down all the way to the simplest process. And the simplest process turns out to be 3 gluon scattering, which doesn't make any sense if they have real momenta, but we can have these momenta be complex and still be on shell to have p squared equals 0. And then this amplitude makes perfect sense, and it's really the building block, and it's totally unambiguous. Feynman vertices depend on the gauge that you choose and are sort of off-shell things, and you need 3 and 4 gluon vertices. But here, you only need this one building block. And so you can implement the BCFW recursion relations on this and get very compact analytic formulas or fast numerical results. And basically, you can do the same sort of thing at the loop level. You can take loop amplitudes, and you can deform the loop momenta here and split the loop integrands into regions where they factorize too. If these are 2 particles and real momenta, this is closely related to ordinary unitarity of the S matrix. But there's also a generalized unitarity, which is also recognized in the 60s, where you put more particles on shell. For example, you can take this left blob and split it up into 2 more, and these are what we call 3-particle cuts. So in this way, we can take these tree blobs and recycle them to generate loop amplitudes. The one thing that we had when we were doing this unitarity in the context of perturbation theory was a knowledge that the loop amplitude is actually a linear combination of certain loop integrals and certain coefficients. And we can compute these loop integrals once and for all, and then when we need a new process, we determine these coefficients using generalized unitarity. So this is a long story, and I'm only giving you a very brief part. There's also a piece called the rational part, which you need, and you can pick up quickly. But there were many programs that were developed around the early 2010s, and some of them have been refined and and more automation has been done. We specialized in vector boson plus multiple jets, getting very large multiplicities. Other groups have more automation involved. This one, bottom open loops, has been a very powerful program recently. But now we can use those and we can get predictions with quantifiable errors. For example, we studied Z plus 1, 2, 3, 4 jets at next to leading order. That's these Black Hat plus Sherpa plots. And you can see they agree quite well for the jet rates as far as we could go. There are some other approaches based on leading order plus Monte Carlo shower that do pretty well too. Their error bands are maybe not the same as ours. They're constrained a bit more. That is, they make certain assumptions when they produce these plots. But we can also predict many differential distributions, and they've measured dozens of differential distributions in many different processes. And everything is generally in pretty good agreement between theory and experiment. This is just a timeline that Gavin Salam put together to illustrate the progress that's been made at one loop, or rather next to leading order. And there was very little progress for a while until around 2006 or so, where people were able to go to 2 goes to 4 through 2 goes to 6 and develop, along with this, a large increase in the number of different processes. Okay, great. So that was all about one loop. And a lot of the developments in one loop sort of, they're still going on, but there was a big period around 2011 to 2013 where a lot happened. So the next frontier is to do the same thing at 2 loops. And with a couple exceptions I'll get to later, the state of the art is mostly stuck at 2 goes to 2. And the problems for 2 loops are not exactly the same as the ones for 1 loop. At 1 loop, I showed you that there was just this finite set of 1 loop integrals, and they could have been done in the 70s. They're more or less all done and all known. But at 2 loops, different processes give rise to integrals that are either simpler or sometimes very complex. And so a lot of the issues have been in trying to understand the 2 loop integrals. The 1 loop case, the worst integral you ever get is what we call a scalar box integral with 4 propagators in it. And those were known since the time at least of the 't Hooft development to be all expressible in terms of logarithms and then one special function called the dilog. In contrast, the 2 loop ones involve certain polylogarithms and even things that are more difficult called elliptic polylogarithms. For example, at 2 loops, if you have massive particles everywhere, then even this very simple looking integral, which we call the sunset integral, which has 3 massive lines here and a generic momentum coming in, that one is not even a straightforward generalization of the dilogarithm. So it's called elliptic. And although there was numerical work on it a long time ago, and that numerical work is suitable for some applications, there's a lot of interest in understanding analytic properties of integrals related to this. For example, this integral appears when you want to compute top production at next to leading order. You get diagrams like this, and these integrals are related to integrals where you cancel out some of the propagators. If you cancel these propagators, you can contract those lines, and then you can see it looks like a sunset. So this sunset is hiding inside top production. Now, top production is already known, TT bar production at NNLO, for about 7 years. It was done numerically, and so that was adequate. But if we want to go to TT bar plus jet, now we have a much more complicated phase space, and we need a better analytic understanding. So that's an example of some of the frontiers to go to next to leading order. There is a class of processes like W production, which is dominated by massless lines. When all of these lines are massless, then the integrals can be done in terms of multiple polylogarithms, which are more straightforward generalizations of the dialogue. And that advance around 2011, 2012, people were able to compute quite a few of these processes, 2 loop amplitudes, and that generated a large class of 2 to 2 processes and an LO. So I showed you an NLO timeline. Here's a NNLO timeline, which is even more detailed and having many specific processes in it. But what you can see, if you could read these here, all these processes up here are essentially 2 goes to 1 processes. And those were much simpler. So the advances in doing these 2-loop integrals allowed the computation of many 2 goes to 2 processes. So the next barrier is to go beyond 2 goes to 2. In order to do that, for 2 goes to 2, you could get away with using Feynman diagrams, but to go beyond that, it's much more efficient to use multi-loop generalized unitarity. There's a lot of progress that I have no time to review. And also you need these very sophisticated methods for multi-scale, multi-loop integration. But if you look at this construction here, you know that trees can be recycled into multi-loops with a little work from your friendly arborist. So the state of the art now is that the first 2-loop 2 goes to 3 amplitudes are being computed, and there was a lot of work over the last few years, especially their analytic formulas for all the cases for pure QCD at the leading order in the number of colors. And those were carried out by a number of groups, but especially the most complete calculations were done by Abroy, Dorman, Sebros, Cordero, Ida, Page, Zung, and Sotnikov. Now, those are the 2-loop amplitudes, but not yet the NNLO cross-section. That is has a lot of other methods that have to be refined to get those cross-sections out. There is another case of 2 goes to 3, in which it's much simpler to go from the amplitude to the cross-section, and that's pp to 3 photons. And that was recently carried out by this group, Chaudhry, Chacon, Mitov, and Poncelet, again in this large N limit. And what you can see here, these green guys are all basically leading order, never mind what the different points are. And here's next to leading order, and here is next to leading order. In this case, the expansion is also very badly behaved, like Higgs production, but by the time you get to next to leading order, you can see that the results are in the ballpark of the measurement from Atlas. So I think this is a real triumph for NNLO beyond 2 to 2, but we'll see a lot more of it as we go forward. I'm going to skip through this for lack of time, but this is just describing a little bit more about how you could how Higgs production was done all the way at NNLO. So I'd like to conclude by saying that we've seen a real revolution in how precise theory we can get for QCD, the underlying physics at the LHC, in order to compute very important hadron collider processes at NLO and NNLO, and even now in some cases at NNLO. This is far beyond what people thought was possible 20 years ago. So it required a new understanding of scattering amplitudes at a formal level and all their analytic properties, as well as some efficient and stable implementation to get the numbers out. And many people, many groups contributed to this progress. In parallel, there's been a lot of progress in understanding amplitudes in supersymmetric gauge theories and also in gravity. And I think later today we'll hear more about that latter topic from Svi Byrne. So this sort of revolution in our understanding of QCD is far from over. There are many, many more processes that await, and we also look forward to all the data that will be produced by the LHC in the coming decade. So thanks a lot.
Okay, thank you very much for this very nice talk. We have time for questions. One by one.
Nobody wants to ask the first question. Maria Elena.
Hey, hi. It's a very nice talk. What do you think about working in parallel in the following sense? You have an experiment that needs your theoretical predictions, and at the same time you want to learn about the fundamental things of the S matrix the amplitudes at all orders. So sometimes there's no time. So you, as a theorist, you get requested these amplitudes at a fixed order, but at the same time you have interest in going beyond and looking at all these nice identities and connections. So for the younger generation, what would you say about this? How would you invest your time?
Well, you really have to choose what is most interesting to you. I balance my time a bit, but every now and then I take a vacation from the real world and I go off and do planar n=4 super Yang-Mills theory because it's much more fun. And I even try to suck irrespectable phenomenologists off into that direction sometimes. And sometimes we learn things and it comes back. But it is a tricky question. As this field has grown, this field of scattering amplitudes, there's an annual conference, which like Lorenzo's been to, and I think it's grown even faster in terms of numbers of people, off in the more formal directions. And I want to try to keep them anchored to the real world somewhat, at least. Well, there's actually two real worlds. There's the LHC real world, and Zvi will probably talk about the LIGO world, because there are also some connections to data in that direction. But when you're young, you have to kind of pick and choose. So it's good to be T-shaped. That is to say, it's good to find an area where you can specialize and drill down deeply. But it's also very good to keep some knowledge across the field, so you can be thinking about where the things you know might be applied somewhere else.
Okay. Some other question? I have one question on something that you touched shortly, and I think you said that you don't need for doing in this unitary part like the ghost.
Yeah.
So in the 80s, in the 90s, in the textbooks where we learn field theory, it was said that we have these different gauges for doing calculations, and the unitary gauge was like non-renormalizable. But I see that in these methods you go to loops. So how is that? Can we have a unitary gauge that is renormalizable?
Well, we're not trying to calculate generic off-shell Green's functions. I think that's probably where the answer lies.
Oh, okay.
That the non-renormalizability would matter if we really wanted generic off-shell Green's function. But when you go on shell and you just restrict to the physical states, you can get back all the things that you wanted to get, or that you got with textbooks and ghosts. So in the textbook calculation of the beta function, the ghosts play a critical role. But there is no reason to do it that way. But you have to do something slightly different. You can do an on-shell calculation that has buried within it the ultraviolet divergences for the beta function. However, it has mixed into it infrared divergences that have to be disentangled. So once you understand the infrared divergences, which are actually related to tree calculations through the overall cancellation of all infrared divergences, you can get the beta function out of an on-shell calculation with no ghosts at all. And so the non-renormalizability never shows up. And I think it's basically because it affects only off-shell Green's functions.
Okay.
Good question. James?
So thank you for a very interesting talk. At one point you mentioned the spinor helicity formalism, and you mentioned obviously the maximally helicity violating amplitudes. But in traditional settings, the spinor helicity formalism was developed for particles which have zero mass. And more recently, there have been some generalizations that can take into account fermions with non-zero mass. I was just wondering whether the techniques that you mentioned are able to be generalized and applied using spinor helicity for massive particles?
Yeah, that's a great question. There were spinor helicity methods for massive fermions in the 80s and so on, but I think the work of Nima or Connie Hamed and Yitin Huang and collaborators was a little more elegant way of putting it in terms of quantities that transform nicely under the massive little group. And those sort of give you the external handles that you need in order to, or they help you in trying to use unitarity. And most things go through pretty well with massive particles, but there is one additional subtlety. When you have only massless particles, you can ignore certain classes of contributions, which are called bubbles on external legs. And those are rather singular because if the external particle, you want it to be exactly on shell, then this internal propagator that connects you to the bubble will also be on shell, and it'll be infinite. So you have to figure out a way around it. Now, if every particle going around the loop is massless, like it was in everything we did, then that bubble integrates to zero. So the fact that you don't know exactly what its integrand is of no consequence. So other groups have been able to handle things with massive particles in them, but they do something slightly different. They have for example, there's a method called the OPP method, and it's not quite as on shell as what we do, and what they do is they do get some gauge dependence in certain terms that allow them to get this. It works fine numerically, so it's not like it's a problem or anything. More recently, there have been some discussions of how to do this in a completely on-shell way by Brito and collaborator in Simon Badger more recently. I haven't studied them in detail, but in some sense you have to go slightly off-shell. You have to kind of take some derivative in some variable in order to handle these massive external bubbles.
Okay, thank you very much.
Sure. Question?
Albert.
Sorry.
You mentioned that in spite of the fact that the coupling is a tenth, you actually have very poor convergence properties. So you need to go to a rather high order. Now that means that the numerical coefficient in front of your powers at 1/10 is larger than you would expect, or naively expect. So my question is, how do you know ahead of time what a decent estimate of that coefficient is, to know how high an order you need to go for the particular process? Is that just estimate on the basis of how many Feynman diagrams you have, or?
There are some hand-waving arguments you can make. They're not very good, but you can kind of estimate them. I mean, oftentimes there are extra logarithms of explicit scales or maybe some implicit scales that show up. One case where you know and you can see that there are large logarithms is if you produce something like the Higgs boson at finite transverse momentum, and you try to take that momentum down to zero. You can just see that there are large logarithms of the ratio of the Higgs to the momentum. And that's called a place where you know that you have to sum up those logarithms. That's called PT resummation. But there's also a similar resummation that's a little bit more hidden in the longitudinal direction called threshold resummation. And it has to do with the fact that when you have two gluons which have a large color charge, they come in and they annihilate to a Higgs which has no color charge. There's a huge amount of sort of breaking radiation, Bremsstrahlung, of gluons that are emitted. And those gluons cause a little mismatch between real and virtual and cause the terms to be large. And so based on the idea that you have large color charge coming in and nothing coming out, you can understand sort of why the correction should be large. But that's just one class of cases where the corrections are large, and I'm not saying you can understand everything that way. But in some cases you can get some intuition. Sometimes it only comes after the fact.
Okay, if there are no more questions, let's thank again Lance for the very nice talk.